Good morning. I am Prasannanjaneya Reddy, working as Assistant Professor in the Department of ECE, Institute of Aeronautical Engineering College, Dundigal, Hyderabad. In this session, we are going to discuss about semaphores and queues. So, what the question is, describe semaphores and queues in ARTAS. How do they assist in task communication? Provide examples. This is the previous question in the semester exams. Semaphore is nothing but a key. Okay. Semaphores is a synchronizing mechanism in concurrent programming. Concurrent means parallel programming, where multiple threads or processes execute simultaneously. Okay. So, ensuring proper coordination and preventing race condition is paramount. Suppose only one resource available. If more than one people want that resource means, at that time, based on priority or based on some algorithm, we are assigning the resource to the particular person. That is requirement here. Here CPU is required for every process to do its operation. So CPU is allocated for the particular process depends on the scheduling algorithms. So which process will get the CPU, that depends on the by using semaphores or scheduling algorithms. A semaphore is a synchronization primitive, essentially a variable that control access to a shared resource, either dashboards, either memory devices, either additional hardware, either communication peripherals, like that. It operates on a simple principle. Okay, it maintains a count that reflects the availability of the resource. Suppose memory device is there. At a time, one person is access that memory device or memory bus, the data bus or address bus or some private peripheral bus, advanced peripheral buses. So, among multiple peripherals, which peripheral will access the communication bus? Which peripheral accessing the memory devices? Which peripheral access the CPU? Which peripheral access the particular hardware or particular things? That will be discussed here by using semaphores. So everyone wants the resource. That is the race condition here. Race condition means at a time multiple persons want the same thing, but because of input from other device, that will be struck. That will be race condition. Here some key operations are wait operation. Means decrement the semaphore count. Okay. When it will decrement semaphore count, if the count becomes negative, the thread or process is blocked until the count becomes non-negative. Okay. Signal operation increments the semaphore count if there are any blocked threads waiting on semaphore, one of them is unblocked. Suppose car parking is there. In car parking, 10 slots are available to park 10 vehicles. Suppose in the beginning, at the time of 0, no vehicle is parked, so 10 slots are available. Okay, semaphore count is 10 at that time. Semaphore count is 10. One by one persons will come and park their vehicles in the parking slot. Suppose 6 persons are coming and parking the 6 vehicles in the parking slot. Then the semaphore count will be reducing. Means the semaphore count is total available, total slots are 10, 6 slots are occupied by the 6 vehicles. So balance is 4. So the 10 count is reduced to the decremented to the 4. Suppose any new persons are coming, again 4 persons are coming, that 4 also occupied by them. Again people are coming means they need to wait until the parking slot is free. And that time the count becomes negative. Semaphore count becomes negative. Suppose any park is left the parking slot means then that negative value -4 to -3. Again one more vehicle is left the parking slot means again -1 decremented means -3 to -2 like that. Based on the number of vehicles left the parking slots, that count will be incremented. Based on the vehicles are looking for parking slot, based on that the count will be reduced. Okay, that is the meaning here. Total 10 parking slots available among 10. So how many vehicles are occupied by parking slots? If 10 vehicles are occupied by 10 vehicle parking slots means the semaphore count is 0. So at that time, if any new vehicle enter into the looking for a slot means that count becomes negative, -1 semaphore count, again -2 as the number of vehicles waiting in the queue. As the waiting list is increases, the negative value increases. Whenever the parking slot is free means again that will be decreased, the count will be decreased. Okay, that is the meaning here. Here different types of semaphores are available. Okay, that is binary semaphore means can take two values. Binary means 2, means either 0 or 1. Acts like a lock, allowing only one thread or process to access a resource at a time. At a time, the studio will be occupied by one faculty only. That's the meaning. Either free or occupied. Free means 1, occupied means 0. Availability 0. Like that. Next, counting semaphore can take on any non-negative integer value, represents the number of available resources. Okay. Coming to the real world analogy, imagine a parking, just now we discussed about parking slot. Imagine a parking lot with a limited number of parking spaces. A counting semaphore can represent the number of available spaces. Semaphore represents the number of available spaces. When a car enters, the count decreases. Whenever any parking slot is occupied by a vehicle, the semaphore value reduces. Means number of available spaces reduces. That's why semaphore count will be reducing here. When a car leaves, the count increases. Means parking slot is free means the semaphore available spaces increases, means semaphore count increases. If all spaces are occupied, the count will be 0. Okay, the availability is 0. So the semaphore value is 0. Incoming cars must wait until a space becomes available. If any new vehicle enter into the parking area, until the parking slot is free, that cars needs to be wait. Okay, that's the thing. So, applications of semaphores. So, we can use semaphores in real-time operating systems for allocating the resources, like communication buses, memory devices, or additional hardware circuits, or CPU. Resource allocation means controlling access to shared resources like printer, files, or database connections. like connecting to the server or connecting to the printer or accessing the files like that. Next, synchronization purpose. Coordinating the execution of multiple threads or processes, ensuring proper order and prevent race conditions. Race condition means like in traffic signal, everyone coming in all directions means what happens? No vehicle will leave left the traffic signal because everyone comes front side, so there is full traffic. There is no way to go to our direction. Okay, that is race conditions. To avoid that one, at a particular point of time, we are allowing the vehicles in one direction only. Otherwise, all vehicles move forward and traffic is stuck and we get inconvenience. Next, deadlock avoidance. So, used in conjunction with other techniques to prevent deadlocks. When two or more threads are indefinitely blocked waiting for each other. Suppose two persons are there or two tasks are there. If you want to do this task, it requires the resource from A. A requires the resource from B. B requires the resource from A. At that time, both are waiting for resources from others, so the task is not completed. That is called deadlock. Suppose task A, task B are there. If you want to do the task A, it requires the data from B. If you want to complete the task B, it requires the data from A. So, both are waiting for resources from each other and no task is completed. That is called deadlock condition. So, to avoid such situations, we can release the data in one side. From A can do first, we can give the priority to A and complete the task or release the resource from A. Okay. Example, consider two threads A and B sharing common buffer. Semaphores can be used to ensure that only one thread accesses the buffer at a time. Here, first, initialize the semaphore, means a semaphore is created with a count of 1. Next, thread. It performs the wait operation on the semaphore. If successful semaphore count is positive, access the buffer. Perform the signal operation on the semaphore, allowing other threads to access the buffer. Thread B, follow the same steps by the A. Next, queue. Like our queues in the railway ticket counters, anywhere, any counters, how we are waiting in the queue, like that. There is the same manner in the queue also in the RTOS. In the context of real-time operating system, queues are fundamental data structures that facilitate communication and synchronization between tasks. They operate on first in first out principle, ensuring that data is processed in the order it was received. So suppose in the ticket counter, whoever is waiting in the first one, they will get the ticket first. In the same manner, first in first out order, the first task will complete. After completing the first one, again we will complete the next task. So key concept of tasks. Independent units of execution within an RTOS. Next, communication means exchanging data or signals between the tasks. Synchronization, coordinating the execution of tasks to maintain system integrity. Queues in the RTOS. In the context of real-time operating system, how queues work in the RTOS. First, create the queue. A queue is created with a specific size, maximum number of elements it can hold. Sending the task. A task sends data to the queue. If the queue is full, the sending task may be blocked until spaces become available. At the receiving side, another task receives the data from the queue. If the queue is empty, the receiving task may be blocked until the data arrives. So first I am sending the data to the queue. Based on the first in first out structure, the queue will send the data to the receiver. Message queues. Suppose I am sending 10 messages from my mobile phone. Whatever the same message I sent first, that will be sent to the corresponding receiver. After sending the first message, again, whatever the next second message, next third message, next fourth message, in the buffer. Like that, it will send the messages. Benefits of queues in real-time operating system. Decoupling. Tasks can operate independently, reducing dependencies and improving system modularity. So it is also used in asynchronous communication, like tasks can exchange data without direct coupling, enabling the flexible timing and responsiveness. Data buffering. Queues can store data temporarily, allowing tasks to process data at their own space. Next, resource sharing purpose. Queues can be used to share the resources, like our message queues or our message inbox, between tasks in controlled manner. Next, synchronization. Queues can be used to synchronize the execution of tasks, ensuring that critical sections are accessed in the correct order. Common use cases. Queues are used in different applications like sensor data acquisition, storing sensor readings for processing by other tasks. I am getting the temperature data, current temperature, current room temperature in the sense for AC, or body temperature for the patient, or humidity some data, or heart rate, whatever the data I want, I will continuously get the corresponding data from the sensors. The data is stored in the message queues. Command and control. Passing command between tasks in a control system. Event handling. Queuing the events for later processing. I am sending, suppose in the laptop or desktop or mobile phone, I am playing some music, playing some game, sending some messages, sending some mails, but I am not waiting. I am doing other tasks. So one by one, the task will be completed. Whatever the first in first order in the queue, the task will be completed. That is the event handling. Data logging. Storing data for analysis or recording, like heartbeat status, temperature status, a patient's information that will be stored and analyzed later whenever you have free time. Examples of sensor data acquisition. A sensor task continuously reads data from sensor. Like, suppose if you switch on the AC means it contains temperature sensor. It continuously measures the current room temperature. So, to maintain the constant room temperature, first we need to know the current room temperature, and that is comparing with the desired room temperature. Based on the difference between current room temperature and desired room temperature, based on the difference, that much of amount of AC valve size is opened. Based on that, that much of cooling air is released into the room. Okay. A sensor task continuously reads data from a sensor. Okay. The sensor task sends the data to the queue. A processing task receives data from the queue and perform calculations. A logging task receives data from the queue and stores it in a file. Key considerations in the messages and semaphores and queues. Queue size. In determining the appropriate queue size is crucial to avoid data loss or excessive blocking. If buffer is full means frequently you are getting some inconvenience. Again resend the data until the receiver receiving the data. So it takes somewhat inconvenience or it takes some time consuming and time waste process by the CPU. So we need to maintain minimum size of the queue. Next, blocking mechanisms. Understanding how tasks are blocked and unblocked when queue are full or empty. We need to observe. So how the message queue is blocked or unblocked. Whenever it is full, is it blocking the incoming data? Or whenever it is empty, it unblocks the data or not? We will check it once. We need to consider while designing that one. Next, priority inversion means ensuring the higher priority tasks are not unduly delayed by lower priority tasks acts in the queue. Suppose A and B are there. A is the highest priority, but A is waiting resource from B. B is lowest priority. At that time, both tasks are not executed because after getting the resource from B, then only A will execute the data, but A is highest priority. So B is blocked by A because of its highest priority. Okay. So by effectively utilizing queues, developers can create a robust and efficient real-time operating system based systems that can handle complex real-time requirements. For this topic, we can refer the textbook is Introduction to Embedded Systems by Shibu KV, published by the Tata McGraw-Hill Education in the 2000.
Like, share and subscribe. Hit the bell icon for more updates.